Okay, so we've already talked about binding energy, but let's just recap it a little bit. So here's our helium nucleus. Okay, there it is. And it's bound together, obviously, into a nucleus. It's held together by the strong force. These two protons are repelling one another, but the strong force dominates because they're so close together, and it holds the nucleus together. Now, we know that this is in a lower potential energy state. This is in a higher potential energy state. Okay, so this is my nucleus. These are the same four individual nucleons, constituent nucleons, dissociated from one another. So what I mean by that is these nucleons are combined together and held together by the strong force. These four are individual nucleons that are not bound together. Okay, so if I want to go from the helium nucleus that's bound together and pull it apart so that we then have the individual nucleons that are dissociated from one another and no longer bound together, the nucleus is in a low potential energy state. The individual nucleons, when they're separated, are in a higher potential energy state. So to get from here to here, I have to input some energy. And the amount of energy I need to input, we worked out before, it's 4.54 times 10 to the minus 12 joules. That's the energy required to pull this nucleus apart, to overcome the strong force, so that the nucleons will be separated from one another. This is the binding energy. Okay? It's the energy required to dissociate the nucleons from one another. Okay, so here's the definition. The binding energy of a nucleus is the energy that has to be supplied, so the energy supplied in order to dissociate a nucleus into its constituent nucleons. So to pull this nucleus apart so that then we have these dissociated nucleons that are individual and not bound together. Don't get confused here. It's not the energy which a nucleus possesses. It's the energy you have to put into a nucleus to pull it apart. The energy you have to provide or supply to pull apart this nucleus. The total energy required to pull a nucleus apart. Okay, so that's the binding energy. You've got to get your head around that before we move on to other more complicated things or further things later on in this topic. The next thing to say is this. Okay, here's your helium nucleus. Okay, but what about a bigger nucleus? Okay, carbon. Okay, so carbon 12-6. Okay, the carbon nucleus is going to consist of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 nucleons. Okay, so 1, 2, 3, 4. Trying to find where to put these. 5. It's probably not a very good diagram this, but it'll do. 6, right? So 1, 2, 3, 4, 5, 6 protons. Bad diagram, but you get the idea, okay? So this nucleus is obviously bigger than the helium nucleus. There's more components to it, okay? This will have a higher binding energy, okay, if we call it the BE. The binding energy of this will be greater than this, okay? So the binding energy of carbon 12, okay, is going to be greater than the binding energy of helium 4, okay? Why is that? Well, there's more nucleons. They're held together by the strong force, okay? And obviously, each of these nucleons is going to require some force to remove it from the nucleus. And in order to apply that force, you've got to supply some energy. So every one of these nucleons is going to require some energy to remove it from the nucleus. There's more nucleons, so overall there's going to be a higher amount of energy required to pull all these nucleons apart into the individual 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So if these are all individual and separated, okay, so the individual protons, to dissociate this carbon nucleus into the 6 individual protons and 6 individual neutrons is going to require more energy than to pull apart these 4 nucleons into their individual constituent parts, okay? Because there are simply more nucleons to pull apart. Each nucleon requires some energy, there's more of them, so in total the binding energy for is going to be greater for a bigger nucleus. So the bigger the nucleus, the bigger the binding energy, okay? Because the more nucleons there are to pull out, so the more total energy required, the higher the total energy required to pull all these nucleons apart into their individual constituent components, okay? So that's binding energy. Talking about binding energy again, we know that the binding energy of helium is 4.54 times 10 to the minus 12 joules. So that means in order to pull all of these nucleons apart, okay, one by one, so pull one out, then another one, then a third one, then a fourth one, the total energy required to do that, so that we pull them all apart into their 4 individual nucleons, is 4.54 times 10 to the minus 12 joules. So that is the binding energy of helium-4. Now, what if you've got a larger nucleus? Let's look at this one here. So here's carbon-12. Sorry for the poor drawing here, but 1, 2, 3, 4, 5, 6 protons, 1, 2, 3, 4, 5, 6 neutrons, okay? So these are our protons, and these are our neutrons, okay? So what about the binding energy for carbon-12? Would you expect it to be more or less than for helium? Well, think about it. For carbon-12, I've got to pull out 12 nucleons. I've got to pull them out one at a time, 12 in total. Okay? Now, each one of those nucleons is bound into the nucleus with the strong force. Okay? Now, to consider here, as the nuclei get bigger, so as the nucleus of a particular element, as you go up the periodic table, you get to higher mass elements, the nucleus of those particular elements becomes larger. Okay? It's not going to take the same amount of energy to pull out each of these individual nucleons, but each individual nucleon is going to require some energy to pull it out. So if you think about it, you've got 12 nucleons here rather than 4. The total energy required to pull out those 12, okay, is going to be more than the total energy required to pull out 4. So I'm going to pull out my proton, then a neutron, then a neutron, then another proton. I'm going to pull out all 12 of those nucleons. It's going to take more energy than to pull out 4 nucleons from helium-4 So to break this nucleus up is going to require more energy than to break up the helium nucleus. So it figures that carbon-12 would have a larger binding energy, and indeed it does, 1.47 times 10 to the minus 11. Okay. But on average, the energy required to pull out one individual nucleon is not the same for each of these nuclei. Okay, or even though this has got a bigger binding energy, the energy required to pull out each individual nucleon isn't the same for each one. Okay. Now the other thing to say is this: as the nuclei get bigger, basically the total binding energy required to pull out all the nucleons gets bigger, because there are more nucleons to pull apart, so the binding energy becomes bigger.